This is part 2 of How Do Rockets Work. We're going to be looking at, remember, two things. How does pressure depend on volume in the rocket as the air expands and the water is pushed out of the rocket? And
So hot. Oh.
the second question is, how do we find the speed of water as it exits the rocket based on the pressure and volume of the air and water in the rocket? Remember, this is our rocket equation. We have mdv dt, that's our classic ma of Newton's second law. Then we have the three forces acting on the rocket, the thrust, drag, and weight. We'll be focusing on this part, thrust, looking for a way to express the velocity of the fuel as it leaves the rocket and the rate of change of the mass of the rocket. First thing we want to know is, what is pressure? Let's take a look at the air in our rocket and water. Here's a depiction of our rocket. We have air on the left and water on the right. And we'll be considering pressure, which we know is the force per unit area on this cross-sectional area right here. We're talking about area A of the surface of the water that we're pushing on. We know pressure is force per area, which means force is the pressure of this gas here times that area. So this raises some interesting questions. If we have this much in purple, gas being displaced, gas expanding as we displace the water, we know if we've done work on this volume, and this is a cylinder, so the volume is the area times the height. Let's call this height delta x, the distance that the gas pushes. Then we're taking our F equals PA, just multiplying both sides by delta x, the distance that we've pushed. So if F is PA, then F delta x is PA delta x. And I noticed something about this A delta x. It's that volume of the purple cylinder, the volume of water we displaced. And that's the force I pushed times how far I pushed it. So let's remember a couple things. This A delta x is the volume, so I have pressure times volume. And over here on the left, force acting along some displacement has a name in physics. We call it work, which I know is also a way that we can change energy. So it seems like the change in energy that happens due to displacing this volume by pushing the water out is going to be equal to the pressure of the gas doing that work times the volume that's been displaced. Taking a look at the units, I have force times delta x, force times distance, is newtons times meters. The unit of pressure is the Pascal, that's a Newton per square meter in SI units, and we're taking pressure times volume, so that's pascals times cubic meters. Now you might remember that a Newton meter has another name. It's the unit of energy called the joule. But let's break it down a little bit further. I know a Newton is force, and force is equal to MA, we can remember. So that's kilograms times meters per second squared. Let's write that out. So a kilogram meter per second squared is a Newton, and we're multiplying by meters. That's a Pascal meter cubed. So what else did we notice? A kilogram meters squared per second squared. Meters squared because I have 2 meters. So mass times meters squared per second squared is mv squared. That reminds us of 1/2 mv squared, our expression for kinetic energy. So we know for sure this is an energy. So we're saying that a joule, the unit of energy, is a Pascal meter cubed. And then dividing by volume on both sides, divide by meters cubed, we can see that a joule per cubic meter is a Pascal. So Pascal means two things. It means both the force per unit area, and when that force actually does work, we see that pressure means the energy per unit volume. So if we pressurize up this volume, we're storing energy. We can see that very clearly from the dimensional analysis here. So, do you want to store a lot of energy? How could we do it? Well, we could have a large volume at high pressure, or we could have a very high pressure even if our volume isn't that big. And those are trade-offs we might have to consider as we pump high pressure air into here to push the water out. There'll be trade-offs for how much volume we can have and how much pressure we can achieve. And we might want to investigate that in some detail.